Chapter 1. Brand new color. What does it look like? Imagine for a moment you're standing in front of a blank canvas, trying to picture a color that has never existed. Go on, give it a try. But soon, you'll probably realize you're just mixing shades you already know. Maybe a blue a bit warmer than usual, a red that's slightly muted. Our minds struggle to think up something totally unseen because our entire experience, every sunset or iris in a flower, every paint in the art store fits within a familiar rainbow pattern of red, orange, yellow, green, blue, indigo, and violet. Every shade we've known fits somewhere into this neat and continuous sequence. But recently, something unusual happened at the University of California, Berkeley. Scientists there made an astonishing claim. They had introduced a completely new color named Olo, a real, actual new color never perceived before. But how could something truly new, something utterly original, possibly join our palette? What sets a genuinely new color apart isn't a careful blend of other existing colors you've seen. Rather, it's when your eyes and brain experience a fundamentally different signal, a sensory input different from all we've biologically experienced before. Normally, your eyes see color by mixing signals from three special kinds of cells known as cone cells: short, medium, and long wavelength cones. It's like they're professional paint mixers, each one responding to different slices of the rainbow. Blue for short cones, green for medium cones, and red for long ones. Your brain cleverly blends their signals, resulting in every color you've ever seen, every color except this newly discovered one. Here's how Berkeley scientists did it. Using a carefully controlled laser setup, they precisely targeted just one specific kind of cone cell, the medium wavelength cones, the cell type responsible normally for perceiving green shades. In everyday life, you never stimulate just one cone in isolation. They're always teaming up, overlapping their work. By directly exciting medium cones alone with a carefully calibrated pulse of laser light, the researchers essentially hacked the usual color recipe and made the participants perceive a truly unique color. It's a bit like hearing a mysterious note right between the keys on a grand piano. Can you imagine how strange that might feel? You've probably heard about forbidden colors before, rumored shades that could supposedly be seen only in rare laboratory experiments or special optical illusions. But those earlier claims were controversial. Critics quickly dismissed them as just clever illusions or mislabeled blends. Nothing genuinely new at all. This time, however, the Berkeley team's method was completely different. Direct stimulation of one specific cone type. When participants first glimpsed Olo with the researchers' high-tech procedure, their reactions were compelling. It was described as intensely saturated, a kind of piercing brilliance, brighter and more vivid than any blue-green shade that nature or even digital screens can reproduce. Not a slightly tweaked version of teal, but an entirely distinct shade that burst beyond the normal constraints of human vision. Word got out quickly. The leaked study title and its exotic color immediately ignited social media, spreading excitement, wonder, and disbelief. Online communities debated and speculated eagerly about what it might actually look like. Memes sprouted overnight, and people engaged in heated online arguments over whether they too would someday witness this new hue with their own eyes. Only 5 individuals have directly experienced Olo, the sturdy volunteers who allowed lasers to hit their eyes. Their emotional reactions ranged from awe and excitement to bewilderment and deep introspection. Each described Olo consistently as beautifully saturated, more intense than they'd ever imagined possible, yet strangely haunting too, knowing they'd never get to see it outside that unique lab setup again. And this leaves a tantalizing question. Could your brain handle the sight of Olo? Would you feel overwhelmed by the unfamiliar intensity? Could it forever change how you see colors you encounter every day? What's extraordinary here isn't magic or sci-fi. It's the stirring possibility that expanding our sensory perceptions might be within our scientific reach. It's a glimpse into human biology that seems at once wildly futuristic and starkly real. Pausing to wonder about all, you might suddenly notice your everyday colors differently. From artists seeking novel forms of beauty, to medical technologists aiming at treatments for vision impairments, Olo hints at deeper worlds waiting patiently just beyond our current capabilities. And this raises yet another intriguing curiosity. If a completely new color is possible, what else about sensory biology haven't we unlocked quite yet? How exactly did biology prepare the eyes and brain for such novelty? Let's take a closer look at the machinery inside our eyes. And in the next chapter, uncover how our biology handles colors, and why the discovery of Olo challenges everything we thought we knew about how our eyes and brains work together. Chapter 2. Why Our Eyes Miss Hidden Shades. When you first open a box of crayons as a child, there's an almost magical quality. With just a few colored crayons, you can make countless shades. 3 sticks of colored wax, a red, a green, and a blue, could blend and produce a nearly infinite rainbow. Our eyes work in a similar way, but the simplicity is deceptive. 3 simple colors making millions may sound incredible, but our eyes take it to another level. Inside, our eyes are 3 types of tiny sensors, commonly called cone cells. Think of each type like those 3 crayons you had as a child: red, green, and blue. Each type of cone cell picks up different wavelengths, or colors, of light. Scientists often call them L cones for long wavelengths, your reds, M cones for medium wavelengths, greens, and S cones for short wavelengths, blues. But let's keep it simple. They're just our red, green, and blue sensors. But here's the thing. Your eyes aren't just counting the signals each cone picks up individually. Your brain compares them. This process is known as opponent processing. Imagine it this way. If 2 cones both detect red strongly, that's clearly red. But if one detects a strong red and another a strong green, your brain compares these 2 signals, mixes them, and decides yellow. It's not reading individual cones in isolation. It's always comparing signals. This comparing setup makes our visual system incredibly efficient, but it also creates natural blind spots. Single cone signals by themselves don't typically reach our conscious perception clearly. In other words, we don't usually see a color purely through the activity of just one cone type, because our brains set up blocks extremely isolated signals. To illustrate this comparison clearly, imagine stopping your car at a typical traffic light. When the green light shines, you don't just get a pure stimulation in your green cones alone. Instead, the red and blue cones also pick up little bits of signal. They overlap a little. Different cones, taken together like an orchestra, not a solo instrument, playing pure notes. Like blending crayons rather than using one crayon completely alone. Now, imagine these cone signals as numeric values from knobs you turn, where each goes from 0 to 10. You could give the setting of your red cone knob to 5, the green to 6, and blue to 1, and your brain determines a familiar color from comparison. Scientists sometimes refer to this comparison system using LMS coordinates, named again after those long red, medium green, and short blue wavelength cones. If you simplified each cone's setting to a numeric reading, colors would be a string of simple coordinates like 5,6.1, a clear numeric signature to every combination. But what's striking is there's one setting we never encounter naturally. A reading like 10 pure stimulation of just one cone without involving others. Never happens in our daily environments because, in reality, light always leaks into neighboring cones. Light wavelengths overlap, so your special human eyes never experience what a single color sensor alone might bring. Each color you ever see is always slightly mixed, always in combination. Think for one moment. If our monitors or paint pigments picked wavelengths that only worked for singular cones without much overlap, we'd have a drastically limited palette. Screens or paints create a multitude of colors precisely because wavelengths overlap, allowing our brains to mix and interpret diverse shades from just three primaries. Technology and art both count on the imperfect blending of neighboring cones. Some intriguing tricks attempt to break these rules. For fleeting seconds, you may know those optical illusions. After images that appear when you stare at bright-colored designs, then shift your gaze to a white wall. Those lingering images sometimes momentarily show shades that feel impossible, a greenish red or reddish green, but still, your cones aren't fully isolated, because even here, there's no true pure cone excitation. Momentary glimpses don't mean true isolation, just the temporary shifts of your cone's sensitivity levels after staring at bright scenes. Why can't we directly show our eye shades from just one cone alone? Well, part of it's the eye's inherent optics. Light entering the eye doesn't travel like a perfectly sharp beam. It scatters slightly, bleeding across neighboring cones, spreading and distributing the stimulation. Think of it like pouring ink on newspaper. No matter how carefully you aim, some ink invariably seeps into nearby fiber. Similar scattering occurs within the delicate environment of our retina, never completely isolating individual cone cells. That's exactly where adaptive optics has stepped in, revolutionizing our ability to see inside our eyes at unprecedented detail. Scientists have made tremendous progress recently by adopting technology initially used for astronomy: adaptive optics. Originally designed to correct blurred starlight observing distant galaxies, adaptive optics systems combine special mirrors and sensitive sensors to remove distortions and sharpen views. Applied to human eyes, this technology can now gaze at individual cone cells in perfect detail. Adaptive optics reshapes light as it enters your eye, correcting for natural distortions caused by your eye's own lens and cornea foremost. These distortions typically scatter incoming light and blur images. With powerful equipment like deformable mirrors, mirrors that subtly adjust and wobble to compensate for errors, scientists have achieved remarkable focus. This complex dance isn't just clever physics, it's clever biology, and it's letting them examine single-cone photoreceptors within a living eye at microscopic scales. Scientists using adaptive optics, or AO, can not only see our cones individually, but also study their distribution and structurally measure their exact responses. Modern techniques, like AO optical coherence tomography, OCT, even capture how cone cells move and respond when a photon of light hits them. With these tools, researchers now observe directly in real time exactly how photoreceptors change and operate in reaction to optical stimulation. It's a true marvel, a glimpse inside living retinal tissue at microscopic resolution, connecting photon events to our incredible human vision. This is not just neat science. It opens doorways into diagnosing and treating previously mysterious eye conditions with unprecedented accuracy. Knowing each cone's exact responses enables clinicians to detect subtle changes long before conventional methods. This revolution in single-cell analysis could reframe our understanding of retinal disorders, perhaps even point us in new therapeutic directions, reshaping ophthalmology and biology textbooks entirely. This breakthrough, the advancement of AO technology, is especially intriguing for the narrative of the device known as Oz you'll soon meet. Adaptive optics is bridging us from a coarse view to something profoundly detailed, something revolutionary. As we've seen over and over in science history, great technological leaps have a tendency to reshape our understanding, changing biology texts, rewriting the rules we hold. Our story, at the crossroads of human biology and technology, now moves to the build process itself, the careful crafting of laser rigs, mirrors, and sensors, the hardware groundwork behind the device Oz. Because sometimes it's a leap in our technical medium that clears a path to entirely new knowledge, and sometimes it's the simplest concepts, a box of crayons mixing their colors, that explain the most subtle complexities of our senses. The wonder is that our senses and our science evolve together, each prompting the next step forward onto something entirely new. Chapter 3. The Gadget That Lets You See Olo. Imagine sitting in a darkened laboratory, surrounded by silence, face carefully positioned before a tabletop device that emits a tiny beam of emerald green sparks straight toward your eye. A pinpoint of green flashing steadily through your pupil, straight onto the landscape of your retina. This is no ordinary sight. It's precision on an almost magical scale. They call it Oz, a name hinting at wizardry, because its operation requires a magician's meticulous accuracy. Every flicker of that green laser has to hit exactly the right spot, no bigger than a fraction of a human hair, and nowhere else. Why such precision? Because each little spark dancing into your retina isn't random. It's directed to activate just one specific set of your color receptors, called cones. Our eyes contain 3 types of cones, each type sensitive to a different range of wavelengths. The short wavelength S cones gently stir when blue light hits them. The medium M cones jump alive in greenish hues, and long L cones awake vividly under reds. To see colors, our brains blend information flowing in from millions of these cones. Normally, every color we experience is the result of cones working together. But Oz takes this idea to an extraordinary extreme. Using what's known as adaptive optics, a technique adapted from astronomy to sharpen blurry telescope images, researchers carefully map every cone in a volunteer's retina. It's like creating a street view map of the retina itself, each of its cones precisely located and distinguished, patient by patient, person by person. Why does it matter? Because to evoke the perception of Olo, a color never before seen, you must stimulate only M cones, not accidentally touching their L or S neighbors. One small error, one stray photon, and the experiment would fail spectacularly. That's what makes Oz so special. It's meticulously selective, picking only the M cones, a feat akin to threading photons through the eye of a needle. The amount of laser light Oz uses is tiny, microdoses of photons, even lower in intensity than the flash from your phone camera. Carefully calibrated, these laser beams flash briefly, keeping participants safe. Yet their wavelengths, precisely tuned, solely activate the medium cones, no neighboring cones, no other type. How is this precision achieved? Oz employs a clever set of steering mirrors, small mirrors controlled electronically, much like a joystick in a video game. Just as a joystick carefully aims and directs your character or your weapon, these mirrors aim and deliver photons exactly where they're supposed to land. They constantly readjust their position to compensate, even for tiny, involuntary eye movements. Such precise calibration also means built-in safety mechanisms. Oz has several safety interlocks and monitors, including eye trackers, which continuously follow the slightest twitch of the participant's eye. These trackers keep adjusting the laser path, automatically redirecting the beam and holding it steadily on the same microscopic spot. Without such advanced checks and balances, Even the minor tremors of a heartbeat could spoil the accuracy, sending photons astray into neighboring cones. To prevent subtle contamination from ambient photons, those loose specks of light sent wandering in all directions, Oz tests happen in absolute darkness. Volunteers spend some time in total dark adaptation before the experiment begins, ensuring that not a single stray photon disturbs the delicate isolation of the laser beam. Each participant undergoes a fascinating yet simple experiment. After a carefully aimed pulse of photons from Oz, they're asked to name the color experienced, over and over, each tiny flash illuminating only M cones. The researchers expected something greenish. M cones typically sense that part of the spectrum. But the result was remarkable. A genuine aha moment happened when all 5 volunteers independently described seeing not just greenish, but an intense and unusual hue. With surprise and excitement, each volunteer wrote down variants of intense teal, a rich blue-green utterly foreign to what's possible from natural surroundings or screens. For the first time in human experience, a purely isolated McCone activation produced this peculiar sensation, an entirely new perception. It was at this revelation that the lead student glanced down at the datasheet, noticing the shorthand they used to indicate green activated only. The coded designation, 0-10. With creativity sparked by the moment's excitement, this numeric shorthand blossomed into the catchy nickname we've adopted, OLO. But once isn't enough for good science. Researchers understood the necessity of surety and repeatability, so each volunteer returned days later. Calibration steps painstakingly performed again and again, confirming stability and replicable accuracy. And the results remained precisely stable. Participants each time reliably saw the same astonishing new color, OLO. Now, here's something curious. As vivid and clear as OLO is, to those who have seen it with Oz, you absolutely cannot see the same color reproduced on your phone or computer screen. Any screen, no matter how advanced, mixes at least 2 cones in your retina, muddying the purity required. Screens always fire a blend of cone signals. OLO's pure unadulterated uniqueness comes strictly from the isolated single-type stimulation. It remains inaccessible to everyday gadgets, another unique twist reinforcing its extraordinary status. But imagine, right now, Oz needs a whole room of precise, delicate equipment. Yet researchers look forward to the day when such technology might shrink from a careful tabletop experiment down to a portable size you might wear on your body. Perhaps even to flexible, corrective, laser-equipped contact lenses. Future devices could isolate colors like OLO in everyday life, not just letting you see an utterly new color, but potentially helping those with color vision deficiencies rediscover colors lost to their eyes. The path is not short, but each discovery takes us a step closer to broad possibilities, beyond the tools and technique. Beyond the intense novel teal itself, what about the people in that quiet lab room who became the world's first to see a wholly unfamiliar hue? Volunteers describe different experiences: delight, surprise, wonder. But invariably, there is awe. Not in seeing color itself, after all, color is a familiar human sensation, but rather awe at suddenly realizing something fundamental. The colors we perceive in our daily lives represent just a small portion of what's possible. One volunteer remarked how it felt almost like finding a hidden door to extra perception they never realized was even locked. Each viewed ordinary visual life differently afterward, subtly reminded that beyond familiar perceptions lie still richer possibilities. Thus, this meticulous invention, known affectionately as Oz, has opened a quiet revolution, giving glimpses not just to a never-before-seen color named OLO, but into the fascinating flexibility and hidden layers of human vision itself. Chapter 4. How Test Pilots Reacted to Olo. It felt like electric sea foam running through my brain. That's how one volunteer described their first look at Olo. This statement captures exactly how elusive and indescribable the sensation was. Imagine color so novel, so unexpected, that your existing vocabulary feels useless in trying to describe it. In the moments before first exposure, the room echoed with nervous laughter. Volunteers shuffled awkwardly in anticipation, jokingly glancing sideways at each other. But after their eyes first saw Olo, an extraordinary hush fell. With that first glimpse, everything changed. In the carefully kept diaries given to each participant, one theme emerged repeatedly. Each observer wrote about colors that shifted endlessly, somewhere between bluish to greenish, yet frustratingly never matching any color chip they had ever seen before. No paint swatch or ink tone captured Olo. It remained beyond their ability to categorize. The color often led to profound confusion, like tasting something perfectly delicious, but having no ingredient list to guide the tongue. Is it sweet? Salty? Something in between? The mind struggled to frame Olo in familiar terms, and utterly failed. The volunteers were even asked to score Olo on standardized subjective color scales. Typically, these scales stop at 100 points for saturation. Astonishingly, every single test pilot ranked Olo well beyond this boundary. Scores clustered near 120 or higher, an impossibility death blow to traditional theories of color perception. How could something exceed our psychological limits? Olo broke many barriers. And volunteers struggled to define an undefinable reality. Physiological reactions were just as fascinating. Cameras captured faces in real time, closely monitoring the volunteers as they encountered Olo. Pupils visibly widened, seemingly hungry to absorb more of this unbelievable sight. Sensitive sensors detected hairline spikes in galvanic skin response, the body's silent cues to awe. Goosebumps covered the skin in subtle waves, mirroring the viewer's inner turmoil of wonder and disbelief. An artist among the volunteers brought their sketch pad along. Moved by a creative reflex, they mixed paint, desperately trying to replicate Olo. With growing disappointment, they repeatedly applied swatches to paper only to cross each one out, muttering softly that each shade was quietly disappointing compared to the electric vibrancy they'd witnessed. This simple action spoke volumes, exposing the profound helplessness of translating an utterly novel stimulation into something tangible. Skepticism surfaced quickly. Could the astonishing reaction be psychological suggestion? A placebo of visual experience? Researchers accounted for this possibility, conducting placebo tests with mere ordinary colored flashes subtly presented as new colors. These placebo tests always failed. Volunteers swiftly identified them as ordinary, none producing the unique emotional or physical effects Olo brought forth. This distinction proved reassuring, but puzzling. Olo evaded explanation or dismissal. It remained genuinely and undeniably new. Most haunting for volunteers was Olo's elusive nature and memory. Hours after the test ended, participants admitted frustration at their utter inability to recall Olo exactly as they had seen it. This wasn't ordinary forgetfulness. Rather, it felt like grasping at smoke, as if their brains lacked the basic tools to retain the memory of a color beyond human normalcy. Without a real reference, no fruit nor flower to anchor this shade in daily experiences, the human brain struggles to recall or reflect upon this pure novelty. In heartfelt comments, many participants expressed emotional yearning. More than one confessed that what they really wanted, the deepest craving in fact, was to bring their closest friends or loved ones to witness what they'd seen. Sharing seemed essential to validating the experience. And this raised ethical questions too. as if a legitimate human need was born within them, one that the experiment offered but might also be taking away. Historically, we've seen similar moments of astonishment among travelers first encountering technology. Sailors returning from voyages in the early 20th century stumbled upon neon lights for the very first time. The news circulated quickly, captivating their entire community. Witnessing lines and shapes glowing vibrantly in shades of electric pinks and blues left them stunned. The unexpected brilliance astonished minds, briefly collapsed vocabularies, and created new societal touchpoints previously unimaginable. Olo provided a similar cultural shock on a smaller scale, today's neon lights for the human eyes. Imagine losing a word, struggling to bring it to the tip of your tongue, knowing exactly what feeling or object you're referring to, yet failing utterly to conjure it. Most of us have felt that familiar frustration. Now consider it magnified manifold, not a missing word or fact, but the very color of a lived experience. Our participants grappled with just such a sensation, an endless loop of quiet frustration stealing repeatedly into their conversations days or even weeks later. Such momentous experiences lead naturally to deeper ethical considerations. If we can introduce elective sensory experiences, colors, flavors, even emotions outside everyday human limitations, should we? What would our consciousness become if we add entirely new reference points to our biology, new ways to experience our surroundings? Are we ready for these offerings? Or would welcoming such novelty fragment our shared humanity? As researchers prepare to extend these findings into broader human social questions, the volunteers who glimpsed Olo continue wondering if they're better or worse off after experiencing something they comprehend so weakly, yet want to share so passionately. Only time, reflection, and disciplined study will determine whether a new color enriches human identity or merely throws wider open the doors of what we realize we'll never fully understand. Chapter 5. Could we add Olo to everyday screens? Imagine future smartphone ads boldly promoting their newest feature. Now with Olo Vision. It sounds like something from science fiction. But could it become reality? Could our everyday screens soon show us colors we've never seen before? Today, nearly all screens around us, from smartphone displays to huge televisions, use the same foundational approach, displaying millions of colors by mixing just 3 tiny lights: red, green, and blue, LEDs. With precise adjustments, these 3 primary colors combine to create the rich images your eyes see. Yet, this 3-color technology has limits. Gently blending these shades can mimic many hues. But there remain subtle situations where it just doesn't capture true reality. Some colors fall just outside the RGB triangle. No matter how much you tweak the levels of LEDs, they just can't be accurately depicted. This shortfall isn't a new discovery. Scientists and engineers have long pondered how to add extra colors to displays. One potential solution? Quad-pixel displays, screens containing a 4th type of subpixel in addition to red, green, and blue. Newer televisions have already tested adding a white or yellow subpixel, allowing them to show brighter images and more vibrant hues. Yet, even these additional pixels still don't truly unlock new colors beyond our basic visual perception. What else could we do? One creative approach skips traditional screens entirely. Picture a display technology that bypasses the screen and beams images straight onto your retina. Using tiny directed lasers, this concept is known as laser retinal projection. Using precise beams, a tiny low-power laser can create brilliantly sharp, colorful pictures directly on the back of your eye. This innovation is especially promising for wearable augmented reality glasses, blending digital images seamlessly into the real view before you. Laser projection could theoretically create colors more vivid and delicate than traditional displays. But could it also unlock entirely new types of vision? To answer that question, we must look inside the eye itself. Human eyes typically use 3 types of color receptors, cells known as cones. Each of your cone types is sensitive to particular wavelengths of light, distinguishing red, green, and blue. Here's where science has taken a fascinating turn. Researchers have recently tried implanting genes in animals' retinas, giving them a 4th cone type, one sensitive to a completely different wavelength. Remarkably, some animals have shown signs of adapting to this new color receptor. Their brains adjust to interpret the extra signals, opening the door to genuine expansion of their visual spectrum. If such gene therapy succeeded in human trials, it would mean creating entirely new colors, literally unseen by unmodified human eyes. But could our technology, displays and smartphones, actually adapt fast enough to support this new biological development? Could practical, consumer-friendly screens soon isolate cones and gently stimulate individual cells on the fly? The concept is compelling, but complex. Precise targeting would mean screens must detect and adjust instantly to each person's eyes, something immensely challenging, yet not necessarily impossible in future adaptive technologies. There's another major upside for such innovations beyond mere novelty: medical treatments. For people born with color blindness, unable to differentiate between certain colors due to missing or weak cones, this could be life-changing. Advanced display systems could potentially rewire the brain's color processing networks by introducing additional sensory cues. Colorblind individuals exposed slowly to tailored colors and signals might retrain their brains, finally making differentiated hues clear to them for the first time. Yet color technology doesn't just transform medicine, it inevitably expands our cultural canvas. Think of the art revolutions these new colors could inspire. Paintings springing to life in genuinely new shades. Future artists might choose from digital palettes exponentially more diverse than ever. Within virtual reality, immersing players and viewers into worlds enhanced by richer, brighter, subtly new shades of color could open countless creative avenues from cinema to gaming and beyond. But optimism often comes with caution. If these advanced displays and genetic innovations do materialize, they may raise ethical concerns. Would richer colors only become accessible to those with greater financial resources? Would we risk creating divisions of sensory perception, enhancing the vision of one group while leaving others behind? Equitable access becomes more important the greater our innovations grow. Moreover, ideas always face regulators concerned about eye safety. Lasers projected directly onto retinas, although typically safe, would require extremely precise standards and careful monitoring. Regulatory frameworks would need careful updating, balancing innovation and safety. Nothing is straightforward when reshaping our senses. Still, let's dream forward. Picture schools decades from now, where students not only learn standard primary colors, but explore many unfamiliar shades, including Olo, as naturally as learning their ABCs. Older generations might struggle to imagine such lessons, but children growing up seeing new colors would find them perfectly ordinary. Additionally, there's intriguing potential in research regarding synesthesia, the fascinating neurological phenomenon where senses intermingle, letting people hear colors or taste shapes. Carefully controlled, precisely crafted screen signals enabling new colors could enhance therapy methods, helping mental health professionals tailor therapeutic experiences through immersive, vivid sensations more clearly than ever imagined. As we muse upon these futuristic opportunities for richer shades, economists also perk up. Advertising is a constant driver behind innovation. It's easy to grasp how businesses might hunger for fresh ways to grab attention. An entirely new color dimension represents untapped marketing terrain, creating powerful incentives for developing and commercializing OLED-enhanced screens. Yet, significant hurdles remain. Advanced retina projection hardware isn't cheap today, and custom solutions, even if they become mainstream, may require personal calibration. Your OLO might not be identical to your neighbor's. Individual perception would need meticulous adjustments, adding complexity and cost. And so, we've returned to curiosity, the quiet, unstoppable force propelling humanity forward. Imagine gazing at a sunset, not seeing familiar oranges and reds, but radically fresh hues you've previously never imagined. The very act of looking becomes new again, prompting us all, scientists, artists, technologists, to reconsider what we see and what we know. Each time we wonder, each advance we embrace, our notions of what it means to see keep stretching ever outward. The universe hasn't changed its colors. It's our understanding that expands, forever transforming how we experience our world.